So we've learned how to calculate the internal energy of a substance, of a system, the change in internal energy, because it's equal to the amount of heat transferred plus the amount of work done on or by the system. We also know, based on our expression of work equal to negative P delta V, that change in internal energy equals heat minus P delta V. So let's say a process occurs, okay? Let's say, a gas expands or a gas compresses, whatever happens. And we want to say how much heat was transferred during that process. We want to solve for Q. So let's solve for Q by adding P delta V to both sides. So we'll get Q equals delta U plus P delta V. Now we can solve for the amount of Q, the amount of heat transferred during this process. This will happen at constant pressure. Notice there's no delta sign in P, which means that P, the pressure, is constant. So if we want to measure the amount of heat transferred at constant pressure, we have a different term that we use to quantify the amount of heat being transferred. And that term we use is enthalpy, which we will denote with an H, a capital letter H. Okay. So therefore, the change in enthalpy of a system is equal to the change in internal energy plus the pressure being applied times the change in volume. And you might be thinking, yo, Shar, why can't we just measure enthalpy, H, directly? Well, the thing is, chemists don't really even know at this point. There are so many things going on in a molecule of oxygen, okay, of O2. There are so many different things occurring between that molecule if we drew like the Lewis structure for it, with electrons and with bond energy and with rotations and all this other stuff going on in that molecule, all this movement, that it's very difficult for us to quantify the amount of enthalpy, heat, that this molecule itself has. So instead, we measure the amount of enthalpy that is changing. How much is the enthalpy changing as the substance moves from one situation or from one state to another? So we will only ever see delta H. Okay? Almost always we'll see delta H, the change in enthalpy. Okay? So let's talk about an example. Okay? Let's say we have a sample of ice, H2O solid, and we let it sit out on a table. Over time, we know that H2O is going to melt and it's going to turn into a liquid. Okay? We know that if we were to represent that with kind of like a particle diagram, we're starting with a solid with the molecules close together, and it's turning into a liquid with the molecules spaced further apart. That's not going to happen by itself. We're going to have to add some energy in order for, kind of these intermolecular attractions, these forces here, let's use a different color, okay, for these to kind of break in order for those H2O molecules to be spread apart. We can measure the enthalpy of that process, the heat required for that process to occur. And in fact, the amount of heat, the enthalpy change for this process is 6.01 kilojoules per mole. Okay? If that was rewritten with a little more space, kilojoules per mole. So whenever you look up values of enthalpy, you'll almost always see them written in units of kilojoules per mole or joules per mole. This can be measured in an experiment. There's no way to figure this out without doing an actual experiment, such as a calorimetry experiment, which we'll talk about later this week, in order to calculate the amount of heat that must be added for this process to occur. So just like we said before, if you wanted to know the enthalpy just of H2O solid, you can't measure the amount of enthalpy that that substance has by itself, existing by itself. But as it changes into a different substance, H2O liquid, we can measure the change in enthalpy, and therefore we can denote how much the enthalpy changed by for the process. Okay? And this makes sense. This value is positive, 6.01. That means, since enthalpy, the change in enthalpy is going to be the enthalpy of the products, your final conditions, minus the enthalpy of the reactants. Okay? That means the enthalpy of the products must be greater than the enthalpy of the reactants. There must be more heat in the end than there was in the beginning. And that makes sense, because these bonds, as we said, these are not going to break by themselves. There has to be some heat added some energy added. Here's my heat. Ooh, okay. Some heat added in order for these bonds to break. Some energy has to come in. Okay. Since delta H is greater than 0, it's positive. That means that this process, we can think about, is it going to be endothermic or exothermic? It's going to be endothermic. Since heat was added, we had to add this heat, this energy here to break these bonds. We entered energy, we added energy in, so this process is endothermic. And we can denote that by saying that delta H is greater than 0. Okay? There's a few key points that you need to know about enthalpy. Okay? Number 1, enthalpy is extensive. That means that it depends on the number of moles or the amount that are present. So if you look at this equation, okay, the coefficients for these are both 1. 1 H2O solid turns into 1 H2O liquid. So for every 1 mole of H2O solid that melts into H2O liquid, that requires 6.01 kilojoules. That's why the units are in kilojoules per mole. But let's say we put a coefficient of 2 in front of these. That's going to change the amount of enthalpy needed for this process to occur. Since we have twice the amount of H2O solid, ice, we're going to need twice the amount of overall kilojoules. So for this process to occur, it would now take 2 times 6.01, which will give you about 12.02 kilojoules for this process to occur. That's still the same thing as 6.01 kilojoules per mole. We're just now taking into account the amount of moles that we have. It's also extremely important that you denote the states of matter so that we make sure that we notice that if something is a solid, a liquid, or a gas. Because the enthalpy change going from a solid to a liquid water is way, way different than the amount of enthalpy change needed to go from H2O liquid to H2O gas. In fact, the enthalpy for that process is much, much, much higher. So be very careful with states of matter. The third property of enthalpy that's extremely important is that if you reverse reaction, flip the sign. So that means if instead of having solid water, solid ice, solid H2O, solid water, turning into liquid H2O, if we flip that reaction around, and let's say we had, H2O liquid turning into H2O solid, okay, that means the amount of enthalpy change in this process, the sign is going to be reversed. So the enthalpy change for this process would no longer be 6.01 kilojoules, but it would be negative 6.01 kilojoules per mole. Okay. And as a result, you can now ask, is that going to be an endothermic or exothermic process? Okay. Well, since delta H is less than 0 now, it's negative, this is going to be an exothermic process. So let's just kind of summarize that on the next page, nice and neat. If delta H is greater than 0, that means enthalpy is being added, heat is being added. This is an endothermic process. Whereas if the change in enthalpy is less than 0, negative, it's going to be an exothermic process. So we have to be able to identify whether a reaction is endothermic or exothermic based on the change in enthalpy. Another way that you'll need to see these reactions, you'll see them is something like this with an arrow on the side that says enthalpy. Okay. And now you'll see how does the enthalpy change for that reaction of H2O solid turning into H2O liquid. So again, this is not like a new type of problem. This is just another way you might see these the amount of energy expressed. Okay, so as we move up here, the idea is that there's more enthalpy in the system. So think about this reaction here, the change in enthalpy was 6.01 kilojoules per mole. So that means at the end, H2O liquid has 6.01 kilojoules more per mole than H2O solid does. That's how much energy it took to turn H2O into a liquid, 1 mole of it. Okay? So that means that H2O liquid relative to H2O solid would be higher up. And for this process to occur, we would have to add heat from the surroundings. Okay? So heat absorbed by system from the surroundings. Okay? And again, that just is consistent with everything we've said. Since heat is absorbed by the system is gaining heat. Again, that makes sense that this is going to be a endothermic reaction, and since it's still positive, it's an endothermic reaction. So if you see a diagram that looks like this, don't be afraid. All it's showing is the relative amounts of enthalpy in the two states, in the products and in the reactants. Okay?